galactic nuclei recognition model based on deep neural network.
Hi everyone, this is about study of Asian recognitions based on deep neural network. I'm the final speaker of today, and I guess you guys are already very tired, so I will finish this talk in a very short time. Okay. And in this talk, I will describe the target of this work, and I will briefly introduce the model I use and the results it gives us. And finally, I will compare my results with the standard SED fitting. Okay. Our target is as follows. We have totally 44 bands at most in NEP field. And for each band, it has a magnitude and an error. Oh. So the whole inputs form 44 by 2 arrays, and we hope that, we hope that once we input this array into neural nets, and it could tell us this object is a star from galaxy or an AGN. Okay, so it is our target here. So the main point of this research is to test that if neural net could work well for AGN recognition problems. And second, we want to test that if this model could perform better or worse compared with the standard SED fitting results. And finally, we could release a reliable star from galaxy or AGN catalog accordingly. And the model of our neural net is look like this. I'm not going to get into the details of this, but I want to show you that the input is just the NEP field observations. So we have array here, we have splicer here, we have Ys here. Totally 44 bands and magnitudes here. Okay. So the input is this array. And then, there are totally 6 layers inside this model. The first 3 layers is called convolutional layers. These 3 layers work as the eye of this model. So it is basically retrieving the information of these arrays. And the pointer?
Yes. You keep pushing, then you can show your pointer.
So this pointer is top button.
If you don't know, it's okay.
The final 3 layers are fully kinetic layers. These 3 layers act as the decision maker of this model. So they take the retrieved high-dimensional information from the top 3 layers and then give out final decisions of this object's classification. And finally, this model output a single scalar outputs range from 0 to 1. And if this value is bigger than 0.5, then we say it is an AGN. If it is less than 0.5, we say it is a star from galaxy. Okay. And I'm going to describe my results. Before this, I want to emphasize that some of the objects are excluded from the chainings. It is called validation sets, about 10% in our label data. So it could help us verify that the model's real performance. Okay. And finally, the result is as follows. In a training, because we are trying to recognize AGN, so we give AGN a very heavy weighting. So the AGN recovering rate jumped to 100% in a very, very short time. Okay, this from here to here is very short. But at this point, the star from galaxies recovering rate is very, very low. It's like it is classified all objects as AGNs, but it is not very good, right? So as the training progressed, well, the AGN recovering rate, the star from galaxy recovering rate will gradually increase, and with some trade-off of the AGN recovering rates. Finally, we terminate these trainings at the point that the accuracy, the AGN recovering rate and star from galaxy recovering rate all hold above 80%. And finally, we realized that neural nets works well for AGN recognition problems. And the accuracy and HUM completeness and styrofoam galaxy completeness are all hold at 85% level. So it is a quite good result. Okay, finally, we are going to compare our results with SED fitting. We are describing comparing the results by RC curve. For RC curve, the curve is more like in upper left. That is the better models. And our deep neural network works like this, and SED fitting works like this. So it is apparently that based on our validation sets, the deep neural network is working more better than SED fitting. So finally, we state that deep neural network is working more accurately than SED fittings. And moreover, because SED fitting requires the observation of far infrared data, so it has more limitations, while deep neural network doesn't have this kind of restriction. Finally, the area under this RC curve on neural nets is 89%, while SED fitting only has 76%. So we state that our method could be better than the traditional method. And that's it. Thank you.
Okay, thank you very much for nice talk. We have plenty time for Q&A. Okay, is any question? I don't see on Slack, but is there a question from local people?
Yeah.
Please.
I have a question. So, do you have any interpretation why SED fitting fails so much and maybe on the other hand it's successful?
Oh, you mean the interpretation?
Machine learning. Yeah, interpretation.
There are several possible results. One of them is, well, in SED fitting is more like fitting a physical curve, and so it is a linear fitting, right? But for neural nets is a very complex model, so it is possible to fit nonlinear relations. So the possible complexity of neural nets is better than SED fitting. Other possibilities could be like, because neural net is model free, but SED fitting is based on model. So of course, neural net is more better because it is not restricted by the visible models. And finally, some results might come from that because the neural net is training based on the spectroscopy and X-ray merged data. So neural net is of course more sensitive to this kind of data. And because of this, so neural net is performing better.
Thank you.
Okay, thank you very much. Any other question? Dennis.
Yes, I have one question. So thank you for the talk. It's very interesting. Within the Stigal code, which is SED, we are including right now some machine learning to some of the long modules, so it will show up on the code. And I was interested to know if you change something in your sample study, do you need to have some new learning, and how long does it take?
Sorry, I don't understand your problem. Do we
Sorry,
have?
can you hear?
I can hear you, but your voice is not very clear. Sorry.
I was asking if you change the sample, what kind of learning do you need to do or redo, and how long does it take?
Sorry, I don't understand.
Yeah, I will write it on the Slack. Sorry.
If you change your sample, how long does it take to newly learn? For machine to learn, newly, and then what kind of change are you going to expect?
If we are using new model, new samples, for example, if we today have additionally 10,000 new samples, then how long does it take to learn it? It actually is very short. If you have good enough machines, then it could be done in like 10 minutes, so it is very efficient. Thank you.
Okay. Any other questions? So if no, probably.
I raise hand.
Miyari-san. Miyari-san, please go ahead.
Okay, I have a question. My understanding is that your output is like a number between 0 and 1.
Yes.
And say if it's more than 0.5, it's AGM.
Yes.
Then my question is that in that framework, is this possible to get some quantitative number like luminosity in infrared contributed by AGN?
Oh, actually, neural nets could not provide any information unless it is Chen. So it could only provide a simple classification result. If we want to know the contribution of AGN, then we need to train a brand new model to do it.
Okay, then you basically can pick up AGNs. Then you basically can do SED fit to the selected AGNs by
Yes.
neural network. And
Yes,
that's a procedure, right?
Yes.
And still it saves you a lot of time and effort to try a SED fit for all.
Yeah.
Is this right?
Oh, I guess so, but I haven't started.
Yeah,
yet.
okay. Thanks.
Okay, thank you very much. Any other questions? We have still time. Okay, so if no questions, maybe it's time to wrap up.